Welcome everyone on site and online to our Digital Physics breakout session. So this is the first of two breakout sessions. Another one will be tomorrow afternoon. And this one is all about technology and geodict with a focus on two-phase flow or relative permeability applying digital physics. So my name is Christian Hinz. I'm going to start off with an introduction on digital rock analysis in Geodict 2024. So an overview and the latest and greatest. And afterwards, I will hand over to our experts, Bobel Danicic and Arno Jacob, who will go through geodict workflows with a focus on relative permeability and beyond. So starting off with a general that we have. So we want to understand our reservoir properties and we want to optimize oil and gas extraction. In order to get a better understanding of our reservoir or the formations that we have, we need to get rock samples. So we need cores drilled from our wells. So with these cores, we typically extract plugs. They can be imaged with an imaging device such as a micro-CT, so that you get a gray value image in 3D. So with that, you can start off in Geodict to do digital rock analysis. This means you can do image processing, you can segment the 3D scan, you can characterize the geometry, and you can predict pore scale digital rock properties. And having done so, you probably want to upscale your results and integrate them into the reservoir scale or the well log scale in order to improve your reservoir management decisions overall. Okay. So, and this digitalization of the spatial core analysis is both meant as a supplement or a substitution to lab scale experiments in order to save time and costs. So at Master Market, we have a digital physics team, and beyond that, we have more experts. So there's us and the team with Lobel, Arne, and me. Then we have various experts with our CEO, Andreas, also our sales leader, Oliver, and beyond that, also in our development, support, and training teams. So we have highly trained staff for all the different things that you may encounter while using Geodict. Okay, so we have a number of clients to provide you with a reference, both in the oil and gas industry and academia and also in other industries. So just some examples. So we may not show all of our client logos here. So we have Shell, Petrobras, we have the OMV, we have also YPF in Argentina, and there's plenty more. And also in other industries, we have automotive industry, filtration batteries. You probably have heard a lot already this morning about these topics. So which is probably the time to get to the question, what are the scales that we are looking at in digital physics? So typically, as I just said, we start off with a plug scale, looking at resolved pore system with a micron resolution in these rocks, so which is about conventional sandstones or the resolved pores and carbonates. But of course, you can also look with digital physics at nanopore systems. So going to nano resolution, you can look or can do digital rocks in shales, can look at the sub-micron carbonate pore systems like micrite, and all the other things like source rocks. So you can have a look at these different scales. Wherever you can resolve the pores, you can do a lot with digital physics. Which is bringing me to the scale where you probably don't resolve the pores, or at least no flow paths in a resolved way, at the whole core scale. So going to the whole core scale up to 500 micron resolution in your CT scans, core CT or medical CT scans. You can do upscaling from the plug scale with Geodict to the whole core scale, for example, with absolute permeability, with different approaches. And that's where we are focusing more and more and advancing from the plug scale towards the whole core scale. So having done all the digital core analysis that you want to do with the samples that you have, we can go probably, you will go to the well log scale and integrate your upscaling results. We've heard a lot about this from Gordon this morning. about upscaling with lab skull data, digital skull, database modeling, and log interpretation. And also you can go to the reservoir scale, integrate your rock property prediction results into reservoir simulators. Let's have a look at the portfolio of Geodict for image processing and image analysis, especially for digital physics. Okay, so starting off, you can import basically any kind of images that you have scanned or taken images of, not limited to micro CT scans or core CT, but also dual energy scans, PIP-SEM, thin sections. It's all a possibility. We highlighted here what's new with Geodict 2024. With image processing, you can do a number of image operations and reduce the noise. The non-local means filter, for example. Image segmentation, you have the typical gray value thresholding approach and the AI segmentation. Also, multimodal segmentation. With image analysis, you can analyze your complete parse system with very many different measures. Can analyze the material distribution in 3D, can do a quality control, and even identify grains, pores, or individual fractures. We've had this already earlier today from Arne presented. And on to this, there's image modeling. So you can generate digital rocks from grain size distributions that you have from a lab or have from a image analysis approach. You can create digital twins from 3D images and even something from 2D images, which will be a topic later. So going from image analysis towards property prediction. With Geodict, you can compute single phase flow to get the absolute permeability of your rocks with a Stokes or Navier-Stokes, and with a Brinkmann term solver applied. You can also do Darcy solver. For two-phase flow, there's capillary pressure curve determination and prediction of the relative permeability related to this. You can compute electrical and thermal properties such as MN exponents. Can compute the mechanical properties, the overall mechanical properties, effective stiffness, fracture propagation, and the quite new piece, PNS wave velocities. And finally, about particle molecule transport, you can compute transport and deposition. And related to this, you can simulate a filter cake formation, or you can go the route with geochemistry and compute reactive flow in a scheme for carbon storage in the underground. Okay, let's go towards latest and greatest. More of a latest slide here, a greatest slide here about imports. So you can basically import 3D images. Here is a Berea sandstone gray values in a cylindrical core. You can import these images, you can filter them. So here you can see the application of a non-local means filter on a carbonate rock, which reduces the noise of the entire image that you see on the left-hand side, but not on the right-hand side, while still keeping the edges sharp and really nice contrast in the image. You can do image segmentation, for example, with a random forest doing the AI labeling. You can also go further with a unit approach, just even enhancing the capabilities of this AI segmentation. Or you can do a gray value thresholding, even with an automated thresholding method. And we also have something new in this respect. So it's been shown earlier this morning, this magic brush for AI labeling, which helps you to determine the edges in a nice manner, in a fast, objective, and reproducible manner. So it probably expedites your labeling process by doing the edges really nicely. So then we have now the Synjection import for RGB images. So if you have RGB images, you can import them sequentially, and you can segment based on all of the 3 representations of a Synjection. So that's possible now with a new Geodict version. And also having this multimodal segmentation, you can work with dual energy scans. So here you have on the right-hand side 60 kV and 120 kV gray values, which look a little different, and you can combine the labeling from both of them, label on both of them, and combine the segmentation with a unit AI segmentation approach to get the most out of your images. So coming down to the possibility to generate 3D microstructures from 2D images. So if you have thin sections of rocks, which is probably one of the fastest and cheapest ways to obtain rock data, or if you have thin section archives that you want to digitalize, you can work with these 2D images. How can you work with them? So we model 3D rocks from just the 2D information that you have available, so that you can perform a 3D digital rock physics on a generated 3D model just from the 2D data that you have available. So this workflow is in an earlier stage, so it's probably not working for all of the complex components you have in a digital rock, but it's already working for one of the more simple things, like here an electrode. You can see the gray values in this case in the segmented image here at the center, which is a really nice 3D representation of this electrode material. So this might work for conventional rock, but if you have a more challenging thin sections that you're looking at, so we would like you to try it out and leave us your feedback so that we can work further on this feature. So we already had to talk about fracture identification earlier today by Arne. So this is something we have on board in Geodict. We also have grain identification, which separates the individual grains in your rock structure so that you get a grain size distribution out of it. As you can see here, having such a grain size distribution, as mentioned earlier, you can also just generate a 3D image based on that. Choose a porosity, generate a 3D image, which is basically a digital twin of what you had. So this works already on board. And having such a generated structure or an imported structure, you can predict the absolute permeability by solving the Stokes equation or the Stokes-Brinkmann or Navier-Stokes-Brinkmann equation, any kind of combination, whatever you need. This is accurate and reproducible. It solves towards a given accuracy, so 99% in this case here for an efficient computation in a 1500 cubic rock. The absolute permeability is determined within 2 hours using 32 parallel cores. So this is highly efficient in terms of runtime and also in terms of memory. Looking at this example here of the Gilderhauser rock, which is from Steffenberg et al. Publication of 2016, we predict the runtime, we predict the absolute permeability with a runtime of 50 minutes or less. So having these kind of data, you can also do upscaling, which brings me to the next slide. So if you have a medical CT data image, all you need is a matrix permeability. So matrix is here this gray material. Then we have the solid material in a bright gray, and we have resolved and isolated pores in here. And if you have a permeability of the porous matrix from a micro CT approach, you can predict the permeability for the entire core in Geodict. And therefore, we have the Darcy solver, which computes the permeability accurately and reproducible again in a runtime of just a matter of minutes for this rock. Whereas the Stokes solver, which of course can also do it, it's a Stokes-Brinkmann solver, so the Brinkmann can handle this matrix, but it's quite unfortunate for the solver, so it takes a little longer. So you can bring down the runtime by a factor 200 by using the Darcy solver. That's the message here. So two-phase flow technologies. So we do simulate two-phase flow with a dynamic pore morphology method, which is a morphological approach that does direct numerical simulation. So you can compute the MICP, which is basically a drainage, or you can compute drainage and imbibition, and for example, an oil-water setup. And doing so, you can consider your rock wettability. So if you know what kind of wettability your rock has, you can assign it, which requires you to distribute the wettability if you have, for example, a mixed wet rock. So if you have a mixed wet rock, we offer you this new GeoApp in Geodict 2024 to simulate the aging process so that you can distribute the wettability. So for example, the oil wet surfaces in your rock based on your settings, basically. So there's also a publication on this from Peter Arnold et al. On favorite options for this, which brings me to the use cases. So what do we have? You can predict the hidden porosity by computing the Tomer-Fit in an MICP setup. You can compute gas trapping curves with Geodict. There's also a nice publication from the OMV And basically, you can predict the primary and the secondary recovery factor, which brings me to this scheme here on the right-hand side showing the capillary pressure curve. So at first the primary drainage, then the spontaneous imbibition, which is more or less the point for the primary recovery factor, looking at this power scale system. And doing the forced imbibition part here, you can predict the secondary recovery factor in a water flooding scheme. So that's what you can do in GeoDict. And you can also predict a secondary drainage based on the endpoint and basically compute the entire hysteresis cycle as you wish. So that's what's available in GeoDict. And having these drainage or imbibition simulations, you can predict the relative permeability for these. You can also investigate the uncertainty by choosing different setups. If you're not, if you want to try different things out. And you can smoothen the curve via an LET fit, as introduced earlier today, which is bringing me probably to this animation here showing a primary drainage. Let's assume the red is oil invading now here Gildenhauser sandstone and displacing water. So also here in the center, you see the computations of the publication of Piet Arnold et al. Showing an uncertainty study at the top using different parameters to set up the imbibition with different visibility distributions and basically the result fitted towards the experiment here at the bottom. So you can see the relative permeability on Y scale and water saturation at the bottom. In red, the oil relative permeability curve, and in blue, the water relative permeability curve. And the experimental points is all these squares here, and the curve computed in GeoDict fits quite well with the experimental data for the Gildenhauser sandstone here. So that's published. Feel free to have a look. So here another explanation of the LET fit. So if you have curves that appear to look like these in GeoDict, which could happen in an unfavorable setting, you can now apply the LET fit to smoothen the curve as shown here towards a smooth curve, which is more reliable and can directly be an input for your reservoir simulator if you use the LET fit in hubs. So related to two-phase flow, you can compute the resistivity index based on a drainage computation, and along with this, the M&N exponents. So can consider even thin water films while doing so on rock surfaces to correct the results in waterbed formations. So this is bringing down your exponents towards a more realistic value, and definitely recommended to do for waterbed formations. So here you can see an image of a GeoDict result. In red, the resistivity index curve, and in blue, the related Archi curve using the Archi's equation. So that's on the right-hand side how an electrical potential would look alike with the oil shown here and the electric potential for the water phase. And colors was increasing potential from blue to red. So being able to do an M&N exponent setup, you can also compute the formation factor with GeoDict by computing the electrical conductivity and applying the according equations. So here's some results for Gildenhauser sandstone. At first, the electrical potential in the rock. So we have a potential difference here applied. And on the right-hand side, the electrical field that's computed, giving you a formation factor in this setting for 42 for the Gildenhauser sandstone. So runtime is pretty low, as you can see. Going further with mechanical properties, you can predict the overall mechanical properties. You can do upscaling. There's a publication from the University of Stanford. You can predict elastic properties of organic-rich source rocks. There's a publication from Mitas and Gupta at the time at Aramco. And they can do deformation setups and also with failure, getting stress strain curves and see where the failure applies and your stress is going downwards. So this can be done in confined, unconfined, uniaxial, triaxial setups. You can consider different mineral strength or different mineral parameters using our material database in Geodict or implementing your own. And which is quite new, also mentioned sometimes today already, is the computation of the P&S wave velocities and the acoustic impedance, which will be a geo app that's upcoming for during this year. Okay, here you can see just as an example the Von Mises stress distribution in 3D for Berea sandstone, bringing me towards the next thing in Geodict, automation. So in Geodict we have a Python interface embedded, so you can automate common repetitive Geodict macros. You can analyze your system's parameter studies, can generate PowerPoint reports, and basically apply the entire range of Python coding directly in Geodict to make complex workflows available to any employee, which makes working a lot easier. Here's just one example for classifying rocks on a porosity permeability plot. So we've just looked at 8 rocks of the same formation, different rocks or different outcrops of a rock, computed porosity permeability for them, and plotted them. We can see pretty nice, for example, how Gildrowhauser sandstone and the Berea sandstone have quite different values for permeability. It can be basically characterized like this. So this is just one example that what you can automate in Geodict. So just with one click, all of this computed and plotted. Which is bringing me to artificial intelligence for digital core analysis in Geodict. So if you have a ground truth, like a pairs of image data and a crowd truth, you can train neural networks for the given task that you're looking at with any number of sample pairs using our Geodict AI module to get a trained model. And you can apply these trained models on your data to reconstruct the ground truth that you've just trained, which is applicable for various use cases like the enhanced image quality, which will be a topic tomorrow. So I'm not going further into detail on this one. And also things like super resolution, mineral mapping, coin identification, whatever you can think of as an application with pairs of ground truth can be done with our Geodict AI workflows. So that you can swap entire workflows to AI, for example, once established. And that's it from my side.
Greetings, everyone. Both you here with us in Kaiserslautern or Ramstein in Germany, and you following us online in this session. First of all, the technical stuff is checked. So we can continue now with 2 workflows in Geodict that you may utilize when you're starting your prediction of different properties. First of the workflows is the quality control of your samples, and the second one is utilization of cylindrical core plugs directly in Geodict and predicting their properties. Let's start with the first workflow here, and let's consider this scenario. You have scanned your rock samples, and you would like to predict some of their properties, such as permeability. And to properly capture the permeability you could predict, you need to have the representative elementary volume of your rock structure. So your structure size has to be sufficiently large, so to say. On the other side, if you go with the structure size that is too large, so to say, you may have you may achieve lesser resolution with your currently available imaging devices. And so there is, we can say, this trade-off between what's the field of view you can achieve and the resolution at the same time. And this is what I would like to highlight here. And in Geodict, we want to tackle these questions. So whether your sample size is good enough to have the REV or representative elementary volume captured, and as well is your image resolution good enough to capture the dominant port road size that affects the predicted permeability later on. This can be done with a few clicks, and I'll now show you the setup of the Geo app directly in Geodict and how the results would look like. So yes, this is just like a key takeaway slide, and let's jump right into Geodict. First of all, can you see the online slide? Okay, screen is visible. I'll be using the already famous Gillehauser sandstone sample from Berg publication. And for setup of this particular GeoApp, we go to the GeoApp menu up here. So GeoApp, and then under the digital rock physics submenu, we can go with the experimental setup. Sorry, quality control. And once you click on the quality control, there is this GeoApp opened here, and we can quickly check what are the functionalities that are being computed to come up with the sample size, quality control, and the voxel throat resolution quality control. By simply clicking on run, we would then compute the results. It would take us maybe 10-15 minutes, depending, of course, also on the sample size. And therefore, I'll now show you the results that I previously computed for this particular sample. So quality control, help me if you see, there it is. Get it. Sandstone quality control. And for this particular sample, so this is the general look of the results you would get. It's the table summarizing, have you passed both of the results, one of them, or if they are in the upper lower boundary, or if one of the so to say criteria is not met. In this case, what I wanted to highlight is exactly this bottom result. So when one of the criteria is not met, and for the further details, we can scroll down in the results and see what is it that is not met. So if we look at the results, we can see that this particular value, which I will go back quickly into the slides as well, of the length is sufficient enough, and that the voxel length to capture the dominant pore throat size is not sufficient in this case. So there's this, we can call it experimental rule of thumb, saying that 10 voxels per throat size would be good enough to have the properly numerical prediction of probability. However, we also found in our studies that already from 4 or more voxels per pore throat are good enough to have the variation approximately 15–20%, of course, depending on the exact structure and setup you have in place. So this would be it. And we can also show the plot, which shows you where your sample permeability and versus porosity lands, and what would be the minimum permeability you could, so to say, predict with this current setup. And in this case, for our sample voxel length, which is 4.4 microns, it's the red line. And if we would look at the current porosity of this sample, we would be able to achieve approximately the minimum of 100 millidarcies permeability prediction.
So thank you very much, Lobel and Christian. I'm going to talk about the advancement in two-phase flow applying digital rock physics in general. And I would like to go more into detail of what was shown by Christian previously. So I'm going to focus on the two-phase flow properties in my part of the talks, which would cover the pore morphology method in general, but also computing capillary pressure curves. With our approach of the pore morphology method, it is also possible to compute not only two-phase flow, but also MICP, which is, generally speaking, not a real two-phase flow because the only phase that is involved is the mercury. We will cover the hysteresis cycle and how it is computed in GeoDict. We will cover relative permeability and also how it is computed and what conclusions can be drawn from the computations. I will cover mixed wettability system and how to set it up, and also a short introduction about gas trapping curves. Let's start with the primary drainage first. So primary drainage like this, you would have a water saturated rock, and in that water saturated rock, we now press oil to displace the water. That is what you could see here. Maybe I replay it. As part of the primary drainage, that is what you just saw, we force oil into our structure until we reach a certain point that is called the point here where you have an irreducible water saturation and a maximum oil saturation for that kind of rock. But why does it matter? You would have to consider the residual oil and water saturation at the same time, because that determines how much oil or gas you can get out of your reservoir as well. And it also gives you valuable information about the pressure you would have to apply to optimize your reservoir. But I would like to also highlight the methods we are using for computing two-phase flow. So two-phase flow in general can be subdivided into non-wetting regimes, wetting regimes, and neutral regimes. If you consider fluid that you put on some kind of surface, that could be either non-wetting, neutral, or wetting. Wetting is usually the case if you put something like water on a table. Then the contact angle is quite low at about 40 degrees. If you have another fluid, the contact angle may be higher, which would then the intermediate state that we call neutral. And in the case of oil, or if you put water on an impregnated jacket or something like that, that water will become non-wetting. Our pore morphology method we are using in GeoDict is based on the Hilbert and Miller method that was invented 2001. And we compute the capillary pressure by using the Young-Laplace equation or the Washburn equation that is also commonly used in the oil and gas industry. In the beginning, we could only distribute oil with a contact angle of 0 degree, which has nothing to do with reality. But based on the pressure, the prediction was quite, let's say, more or less correct. In the original state, when you have something like a structure and you want to drain the water from that structure by a fluid, a non-wetting fluid like oil, we start off by an original state. In the pore morphology method, we then initialize the next step by putting the non-wetting fluid inside of the pores of the reservoir and dilating the material which we want to wet by a certain diameter that goes into the Young-Laplace equation here. Then we check the connectivity afterwards to the inlet, so the direction where the oil is pushed into the structure. We erode back the dilation material radius, and then we will obtain the new status, which has then a higher saturation than compared to the previous state. We also advanced that method even further by not only being able to compute the drainage, but also to model the trap phases, considering the right contact angles, and also considering multiple contact angles at the same time during one simulation. For example, you can see here that we have quartz that is only gray, and then we have these dark areas. And these darker areas have another contact angle compared to the light gray quartz values. And if you run a simulation like that, it would look like this. You increase the pressure even further. And at a certain point, you have these large saturation jumps that completely saturate your structure on top. And that is where the dynamic pore morphology method was invented for. With the dynamic pore morphology method, you can also display the intermediate steps during these burst events. And you can also have a burst, touching, and overlapping events. You can see here on the left-hand side as burst event. In the middle here is overlapping event, and also touching events. And you see that a variety of different intermediate steps are also displayed here, which gives us valuable information about like the progression the oil does during the drainage process. We have also validated our method with an experiment from the University of Saarland with a group from Professor Ralf Scheemann and Dr. Michael Young. And what we did is we did a digital twin for the 2D experiment they had in the lab. The experiment consisted of cylinders with 32 micrometer diameter. That is the round things you can see here within the structure. And these cylinders were held together by plexiglass screens with a 90 degrees contact angle. And then during the experiment, we had different kinds of fluids entering the structure with different contact angle, namely 46 degrees, 100 degrees, and the non-wetting 125 degrees. So this is the comparison we have between our experiment and the simulations that were done by Geodict. The left case would be the wetting case. In the middle, we would have the neutral case, and on the right-hand side, you have the non-wetting case. As the pore morphology method is a quasi-static and a non-dynamic method, these videos are synchronized with respect to saturation, but not with time. And as you can see, you can also see how the surface flips as soon as they are touching the cylinders here. We have also done a plot for that, which is the normalized interfacial area between the wetting and the non-wetting fluid, and the saturation between simulation and experiment, of course, then. And as you can see, the fit is quite well. There are some deviations that can also come from the experiment, but also from the experimental setup within the simulations, as the resolution is also a topic here. But the fitting was quite well for that. As I was mentioning earlier, we are also having applications for Satudict for MICP, which is more or less directly comparable to a lab experiment of an MICP. And with the MICP we offer, you can also compute the Tomer model, which could predict the unresolved porosity that is hidden by the resolution you have obtained by your imaging method. So for example, for the Gildehauser sandstone, we have well-resolved pores, but due to the partial volume effect, not all pores or not the complete porosity that is there is displayed in the simulation. And that is where the Tomer fit comes in, which can then predict the unresolved porosity based on an MICP simulation. And I think it is not displayed here for the Gildehauser, but in this case, the unresolved porosity would be between 2 and 3% of the whole porosity. New in Geodict 2024 would be not only mercury intrusion, but also mercury extrusion simulations that became available right now. So on the top right-hand side, you could see how a conventional mercury intrusion would look like. So you force mercury into the pores of your sample until the sample is fully saturated. Then you release the pressure, and after that you have mercury parts left within the pore structures. So mercury gets trapped within the pore structures, which is here displayed as these red visualized mercury saturation. And if you plot the capillary pressure curve, you can also see that the mercury intrusion is displayed here as a red curve until the structure is fully saturated, and by releasing the pressure, some of the mercury gets trapped within the pore holes. Looking at the procedure in 2D, we have the same behavior. So you increase the pressure until all of these 3 pores are saturated, and by releasing the pressure, some parts of the mercury are trapped within the pore space, all but the larger ones are released. An application for that would be in the oil and gas industry if you compute gas trapping curves, where you are considering different initial gas saturations. And based on these initial gas saturations, you can then obtain the residual gas saturation after the gas is allowed to leave the structure. And the phenomena is quite simple. The more gas you have initially, the more gas is left as a residual gas saturation. And that was also validated by the LAND model. And our simulations were validated with the LAND model, and you can see that these plots are fitting quite well here. I would also like to talk very briefly, because of the sake of time, about the history of the method we have in GeoDict with the pore morphology method, which shows you like the highlights of the development progress for that method. As I was mentioning before, the first method introduced by Hilbert and Miller in 2001, with mercury intrusion capillary pressure becoming available in GeoDict. Then we invented to compute K relative permeability for drainage in water wedge rocks. Then we also included that you would have residual oil and water saturation for your relative permeability computation. Then, as I was mentioning before in one of the videos, we would also, or we made it available to assume different contact angles within the structure. Like I was showing you before with the experiments, we introduced also dynamic fluid interface movement, where you can control how far with each pressure step the saturation can go. That basically defines how many points for the capillary pressure curve you would get. Then introduction of mixed wet rocks, or mixed wettability in general. The implementation of the true contact angle method, which accounts for the true contact angles that were usually a little lower than expected. And then this year, mercury extrusion capillary pressure and LET fit, as it was mentioned by Christian before. I would also like to do a short hands-on for how to compute capillary pressure curves in GeoDict, where we would learn to set up a capillary pressure curve simulation, run the simulation, and interpret the results for that. Basically, we would start with a Gildhauser structure that is well known here. We would push oil inside of the structure, obtain the capillary pressure curve, and we will also obtain a saturated structure where we would also have residual water saturation. So I would also like to start off with that Gildhauser sandstone that Lobel was showing before. To compute a capillary pressure curve, you would have to go to the SatGedict module in the predict menu here. And the first module you can choose from is already the capillary pressure command. By default, in the oil and gas industry, or in the oil and gas edition of GeoDict, you would have the contact angle mode, interfacial surface tension, invading and displaced fluid, set by the needs of the oil and gas industry, which would be oil and water or brine in general. And also the contact angles will be arranged accordingly. So in that case now, we're having water that is saturating the structure by 100%. And SatradIct automatically detects that this fluid will be displaced, as I was already choosing that the invading fluid would be oil. Now I would have to assign a contact angle for the oil on the quartz surface compared to water. So I'm looking at the table here where it says invading fluid contact angle, and have a look at the contact angle I would like to assume for the oil, which is in that case 140 degrees, which can be assumed for oil. So that parameter is already correct. On the other hand side, for the displaced fluid, which is in that case water, 40 degrees would be also correct. If I move to the next tab, SatradIct automatically detects which kind of experiment you want to run. So I cannot click one of these checkboxes here. These checkboxes are set automatically by SatradIct, and it automatically and also detected that it is a drainage in the forced regime I want to do a simulation on. I can check the checkbox here for I want to have my displaced fluid that can leave a residual, which means I would have irreducible water saturation after my simulation. So I want to have this checkbox checked. In the case of an MICP, I would like to simulate, I can uncheck that, but that is only for MICP applications when I consider vacuum to be within my pore space. I can only also select from which boundary side I would like to enter. Have my oil entering the structure. And in that case, I want to have my oil entering only from one side, which is Z-. All the other sides will be connected to somehow a water reservoir. I would not have to change anything here in the solver parameters as they are currently perfectly set up for that kind of purpose. And what I personally like very much about GeoDict is that you are giving references and equations by the solvers directly. So I have all the references and publications listed directly in the modules as well. And also a short definition of how the contact angle is defined in GeoDict and which equations are used. If I now hit run, it runs that capillary pressure curve, but also for the sake of time, I've prepared the drainage experiment beforehand, which you can directly load here. And what we see first would be the report for the saturation, invading saturation, and the capillary pressure that has to be applied to force the oil inside of your structure. And I will have all intermediate structures here available in the GeoDict software. So for each of these saturation steps, I can load each individual pressure step that was executed for that structure. And as you can see, I would have an end saturation of 81 or until about 82% oil, while the rest would be irreducible water saturation that stays within the structure. I can also display the capillary pressure curve. And as you can see, we have that nice plateau here until it reaches a certain point where it cannot saturate the structure anymore. And the rest on the left-hand side here would then be the irreducible water saturation that prevents the oil from moving also to the narrower ports in the pore space. So the next topic I would like to talk about is simulating aging within GeoDict environment. As Gordon was mentioning before in his talk as well, was that we are having different methods available of how we can apply aging to our digital rock samples. Gordon was mentioning two of them because two of them are validated by a publication that was done by Pitt Arnold, but also within the joint collaboration between Math to Market at OMV and Montana University Leoben. That would be the two to the right here. And there's also a very simple approach where you consider the pores or the grain surfaces to become oil wet as soon as oil touches these surfaces. So that is why we call it simple approach, because the algorithm is quite simple. For the stochastic approach, we are using a Gaussian random field to distribute different contact angles within the pore space environment. So it is not based on the oil distribution within the pore space, but on the stochastic probability or on the stochastic distribution of these mixed wet surfaces, while it does not consider the oil saturation here. Gordon was also mentioning the deterministic approach, which considers, based on the pore throat size and the surfaces that are touched by the oil, only the larger pores as oil wet after aging. So in simpler words, you have a parameter that is called pore space considered, and based on that parameter, you can change the wettability of the larger pores within the pore structure. So as you can see here, we have oil that invaded the structure, and only in the larger pores, in 40% of the larger pores of these pore areas, we consider the surfaces of the grains to become oil wet after our drainage. On the right-hand side, you can see an even simpler illustration of that. You would have a size distribution. You consider only the larger pores here, marked in red. And based on these largest pores, which is here in that case 40%, you reassign the contact angles of the grain surfaces then to become oil wet after the drainage. I would also like to show that aging GeoApp in GeoDict as well. I have to hurry up a little, so I make it a little faster here. The GeoApp menu, as Lobel was already introducing, you can simply choose digital rock physics and two-phase flow. There you would have MICP, porous plate, capillary pressure, hysteresis, trapping curve, and simulate aging, the app we are now looking at. You can choose a result file name, which is quite straightforward, a result geometry name, and you can choose from these three different kinds of methods I was just explaining to you in the presentation: deterministic, stochastic, and simple. Then you have to choose which phase that is present in the structure you consider to be the water and the oil phase, and also the volume of the pore space that has to be considered to become oil wet after the drainage. If I run that algorithm, I would obtain an oil wet structure or mixed wet structure. That looks like this. So I have water and oil within my structure, but I have also these oil wet contact angles that are here marked in red. As you can tell from the material information table here, you can see that we have quartz as idea number 1, and we have the same quartz but oil wet in the structure as well. And that is only for now 40% of the larger pores within the structure. And we know also from experimental validation that only larger pores change their wettability after the drainage or during the aging event. That I would like to go back to the presentation as well. And that is why I was explaining the aging GeoApp beforehand or before the imbibition, because that would be the next part of the hysteresis cycle we would like to talk about now. Imbibition would be we released the pressure that was put or at the pressure at which the oil was pushed inside of your structure. And by releasing that pressure, the water floats back into your structure. That is usually called a spontaneous imbibition. But if we then start like water flooding and we also start pushing water into our structure, that imbibition then becomes forced because we apply an external pressure. the structure as well. I also mentioned the imbibition mixed wet stuff. The relative permeability you would compute on the imbibition process would be run on parts of the saturations you would obtain from the imbibition process. So you have water that is pushed inside of your oil wet structure, displacing the oil. And based on the distribution of each of the two phases, you get a relative permeability for both phases based on their saturation. The problem, and what we already were talking about, is in that case the representative elementary volume you would need for two-phase flow. So when do I consider my structure to be representative for a whole reservoir phase that I would like to analyze? Or when can I smoothen out these microscopic or lithology effects? So the scale I would like to be in would be here that REV scale for two-phase flow. And we know from simulations and experiments that that REV scale can be different for different kinds of parameters we are looking at. So for absolute permeability, for example, the REV size I have to consider can be smaller compared to two-phase flow. Usually in the oil and gas industry, you have to analyze hundreds of core samples for relative permeability. And the problem is that in the laboratory, you cannot use the samples anymore after you have done your experiments for measuring the relative permeability on. That is a problem there, which we do not have when we are using an imaging method. And also when we're using simulation, because we wouldn't destroy any of the samples. And we have also an advantage because we can compute very fast. Since computational power increased in the recent years and we have also cloud computing available, we can start multiple instances of relative permeability computations that would, if executed sequentially, would take a long time. But if we execute them at the same time, it would only take about 3 days or so. But how is the relative permeability computed in GeoDict? So as I was mentioning before, we have a quasi-static method for distributing the phases during two-phase flow. On the right-hand side, you can see how that would look like. So in that case, you can see the water phase with different fluid flow velocities flowing around these oil droplets that are clogging the pore space and reducing the permeability for the water phase in that case. So the oil basically closes the flow channels for the water. So permeability for the water phase goes down here. Now we compute the relative permeability based on the effective permeability we have divided by the absolute permeability of the whole sample. And we do that for each phase individually. As I was mentioning before, considering mixed wet condition is crucial to obtain correct results. On the left-hand side, you can see the previous method in the pore morphology method, where we didn't consider any wettability changes after the drainage. And as you can see, the relative permeability curves are, compared to the experimental curves, far off what we have measured in the lab. Now, by considering these wettability changes, you can see that in the case of using the stochastic and the deterministic approach, we have a quite well match with experiment if we consider these mixed wettability approaches we are using in GeoDict compared to the experiments. We can do that not only for these outcrops of samples, but also for whole core plugs. And in that case, I would like to show you how an oil wet relative permeability curve would look like compared to mixed wet and water wet permeability curves. You can see that these crossing points are as well as you would expect them. Water wet crossing point would be most to the right, while the oil wet would be more to the left. We have run the simulation in 20 hours in total. So we have run all 3 of these simulations simultaneously, and each of the simulations took 20 hours. So after one day, you could be finished off by simulating permeability for a core plug like that here. As Christian was mentioning before, you can also apply the LET fit to obtain not only no other way around. You can also play around with the deterministic and stochastic approach parameters that we expose to the graphical user interface in GeoDict to do some kind of sensitivity study. As you can see here in the plots, many of the parameters here were varied, and basically you get a distribution of different relative permeabilities if you run a variety of different parameters for pores that are considered to change the wettability after the drainage of the water, or the stochastic distributed contact angles within the structure. And we found out that for that type of rock, so for conventional rocks, a solid volume percentage of 35% for the stochastic approach is quite, or matches quite well with the experiment. And for the deterministic approach, 75% of the largest pores that are considered to change their wettability give you also a very good match compared to experiments. We can also rely on different methods that we're using as boundary conditions. So you would know the experimental conditions, as you are not able to do experiments right in your reservoir for two-phase flow applications. You can only do it in the lab. So that is why you would be here on the right-hand side, where you consider your structure to be encased with a string sleeve, or to be in an experimental setup where the structure has some kind of tangential boundary conditions that is closed. And on that slide, I would like to show you how different the relative permeability would look like by only considering different boundary conditions. And what we can do is we cannot only consider these encased cases here, like the ones you would have in the lab, but we can also simulate the reservoir conditions, because we are not limited to the structure size. We can also assume that we're having symmetrical boundary conditions or periodic boundary conditions in the tangential directions. I think for the sake of time, I will only explain very briefly that the LET fit not only smoothens your curve out, but it also keeps it takes the irreducible water and oil saturation into account for that fit. So it is not basically only a mathematical model that fits somehow the curves, but it is also a fit that was designed only for the application to fit relative permeability curves. And I would like to show you how to set up a relative permeability curve in GeoDict. So as an input, you would have the structures that I obtained from my imbibition process. So different saturations of oil and water. And based on these structures, I can now compute the effective or the relative permeability for each of these saturation steps to obtain the relative permeability curve you can see here on the right. In GeoDict, we have a hysteresis geo app, which we call a one-click solution. And in that hysteresis geo app, you can execute the whole hysteresis cycle by only one click. So what you simply do is you set up the simulation parameters you are using for the drainage. So the fluid you would like to enter your structure during drainage, and also the fluid that should be displaced by the oil. You can choose the invading sites, from which side the fluids enter during drainage and imbibition. You can choose the contact angles, but also in a mixed wet scenario, you can choose how the contact angles should be changed after your drainage. You can choose, as in the aging GeoApp, the aging method you're using after your drainage. And you can even compute the relative permeability for the imbibition process directly within that geodict environment. So in principle, this is like the all-in-one solution if you want to compute relative permeability for your samples.
Thank you once again, ladies and gentlemen. And let's continue now with another application of two-phase flow module in GeoDict. So let's continue with the computation of resistivity indices and M&N or Archie exponents. Just to give you a short overview why this is important, without giving much too of the details that will be saved for today's session. I would like to say that Archie is low, and the computation of resistivity indices is one of the main applications is in determination of reservoir oil saturations. So Gus Archie came up with the principal equation based on the experimental analysis back in 1942 that relates the measured rock resistivity with the saturations present in the rock, depending on the exponents that intricately link the rock's properties. And now, without getting too much into details for the sake of time, I would like to focus on the approach itself that Archie used in experiments and that are being nowadays as well used, and that we mimic with our digital experiment here. So to determine the Archie exponents, the experiment itself starts from the fully water-saturated rock sample that is being drained by oil. And at the different saturation steps, you measure the coarse resistivity. And then by plotting the measured saturations versus the resistivity indices, you determine the M&N exponents, which finally you can use in the fitting of the Archie's equation to predict the saturation from resistivity log. The similar approach, the experimental setup is being done as for the experimental setup is being done in GeoDict. And we start with simulating the drainage process and then also computing the conductivities at different saturations. Finally, we fit the Archie's equation and you get the value of M&N exponents. What I just said, this is being computed for instance, fall structure where different conductivity properties are assigned for different materials such as brine, oil, water, and and then the computations go into predicting the resistivity index and subsequently coming with the M&N or simulation saturation exponents. The numerics behind involve solving the Laplace equation as a linear set of equations, and by solving the Ohm's law for the same application. Now, what we also had seen is that, for instance, if you look at the micro scale and you observe what are the resistivities that come up in the experiments and what you simulate, we have observed that with the inclusion of thin water films that are that are on the rock surface, you're matching much better your predicted M&N exponents with what behavior you would expect. And this whole workflow, what I want to highlight here is depending, of course, on the sample size and the other parameters. Most of the time it's finished in the hour's time. So that is something what's a huge difference compared to the current experimental setups. And now let's jump right into the GEDIC to show you the setup. Yes, so how the setup would go is with your rock structure, we would go into the predict menu and then set predict. As I mentioned, the first step is predicting the drainage experiment, and that is what Arne has already shown us in one of his sessions. And after the setup of the drainage experiment and running it, we would then go into another SetPredict module called resistivity index, and then go into the setup. From there, we could go ahead and select the results, for instance, what we computed from the drainage, and then set the next set of parameters, such as what I mentioned, the conductivity of either of the phases, such as, for instance, water conductivity, quartz, or oil. So in most of the scenarios, oil and the quartz conductivities are considered as zero. So in that sense, we wouldn't have here much of the alternation. Then you could enable the thin film of water and consider different thickness of such a thin film, which could range depending on what you could also maybe try and match with your experimental results if you had any, or I, from the experience, would go with 20 maybe. Good. Then the setup of boundary conditions and flow direction. And what's over for now, for the sake of time, we could go with default. And then by clicking on run, we would get the results. So also briefly, just I would show you the results here. And this is it. You will get the tables of the predicted saturation and cementation exponents, as well as the table of resistivity indices, with also in the direction that you use to compute. In that case, we had the Z direction, the relative electrical conductivities. Additionally, I would just briefly mention that you get also the plot of what I mentioned, different saturation points where the conductivities have been measured or computed during the experiment itself. That's it. Thank you.